So the last concept we're covering in this chapter is called the polarization of light. Now, we've talked previously about polarization in terms of charges and like if electrons move from one side of an atom to another. We talked about charge polarization. That's not what we're talking about here. So light, we know light are electromagnetic waves. These electromagnetic waves have an electric field portion and a magnetic field portion. When we talk about light being polarized, and by the way, we're talking about specifically linear polarization, light being polarized means that the electric field portion of the wave is oriented in one specific direction. So I've pulled this figure from our textbook. This top picture, vertical polarization, because if we look at the electric field portion oscillating up and down in that y direction, we say that this light wave is vertically polarized. Or just we would represent an up and down arrow to represent that the electric field of this wave is specifically oscillating up and down. In the second example, the horizontal polarization, the electric field is in the x direction. That's not a very good x direction. So this is horizontally polarized. The electric field in this wave just oscillates back and forth in the x direction. The magnetic field is oscillating perpendicularly to that, of course, but keep in mind the electric field is always 3 times 10 to the 8th bigger than the magnetic field. So we had this relationship, I crossed out the B, sorry. This relationship from a previous section, the electric field is the one that is the largest. So when we talk about light being polarized, so polarized light means that the electric field portion of the wave oscillates in one direction only. Now, not all light is polarized. In fact, light from the sun is unpolarized. That means the light is not oscillating only in one direction. We would represent that as not only up and down electric field arrows, but also right and left. Technically, we could write it as a whole bunch of different directions. But we can think of the electric field, all of these as vectors that could be thought of as components in the up and down or side to side directions. Now, just so you know, when we come to the right over here where we were talking about vertically polarized light and horizontally polarized light, that's not the only direction that light can be polarized in. These are just 2 examples. So this is what we're going to talk about in this last section, and that is this polarization. I do want to show a little video clip to give you an idea of what we're looking at. So this one comes from UCLA.
Now, you might be wondering, is light a transverse or a longitudinal wave? How could we test this? This device is called a polarizer. It's designed to let waves get through in only one direction. As I send the wave out, it gets through fine that way, but this way, I can't get the wave through. No matter what crazy wave I send, only the left and right components get through. It's been polarized. Now that only works on transverse waves. If it works on light, then light is a transverse wave. Because light can be polarized, we know it's a transverse wave. This is a polarizer. It's polarizing up and down. This is another polarizer. It's polarizing left and right. When these two are crossed, we get absolute darkness, zero transmittance. But if we cross them the other way, light still gets through. They're polarizing together the same way. Unpolarized light, for example, from the sun, travels to a polarizer, which polarizes it up and down. The light continues and hits another polarizer, but this polarizer is side to side. That cancels all the light. No light gets through.
Okay. When we talk about a polarizer, another term for it is a polarizing filter. The polarizer will have a specific axis. So this is called the filter axis. It does not need to be oriented up and down. It can be oriented in any direction I want to hold it. But what this axis represents is the component. It allows the component of electric field that is parallel to it, to pass through. So if I started with unpolarized light, again, unpolarized light has electric fields in all different directions. So this is made up of a bunch of different waves. All of the waves have different orientations of their electric field. This is called unpolarized light. If you recall back to working with vectors in general, if I have a vector that's at some angle, I can say it has vertical components and horizontal components. And so roughly this unpolarized light is half vertical components and half horizontal components. If I shine unpolarized light on this filter, the light that is transmitted, the light that comes through, is now polarized, and it is polarized with the same direction as this filter axis. So if I had unpolarized light, again, and the axis of our filter horizontal instead. So unpolarized light on our filter, the light that would make it through would be horizontal. this is considered polarized because now the electric field is all completely in one direction. It doesn't matter if, unpolarized light, if our filter axis is at some angle that's not vertical, that's not horizontal, the light that makes it through will be lined up with the axis of the filter. So the line I have drawn in the square has represented the filter axis. So filter axis, filter axis. And that always represents the portion of the electric field or the components of the electric field that can pass through. Any time that we shine unpolarized light on a filter, the intensity of the transmitted light, so intensity, is equal to half of whatever the original unpolarized light intensity is. The transmitted light down here is 1/2 of the original intensity of this unpolarized light. So even the bottom example, the transmitted light, the light that makes it through that we can still see, is half of the original intensity. This is always true for unpolarized light shining on a filter. We will always end up with half of the intensity that we started with. Now it's different if we start with light that is already polarized. I'm going to grab a picture from our textbook to show this better. Okay, so jumping over here, suppose we have polarized light that's shining on a filter. This solid dark electric field line in this picture is representing the polarized light that is shining on the filter. So it's showing us that the components of the electric field of the polarized light is at that angle from vertical. But we can think of this electric field as having a vertical component, which they have represented in here, the E naught cosine theta component. So this up and down, and a horizontal component, this E naught sine theta. So just like any vector, we can break into components, cosine and sine, using our right triangles. The axis of this filter is vertical. That tells me that this original polarized light, so original polarized light with intensity I naught shining on this filter, the only components that will make it through are the vertical components, because those are the ones that line up with this filter's axis. So the E naught cosine theta components are the ones that make it through. Now in terms of intensity, so this is our transmitted light, the light that makes it through the filter. this transmitted light, if you recall, intensity with our electromagnetic waves, intensity is always related to E naught squared. So it turns out we find that the transmitted light can be calculated by knowing the original intensity of this polarized light, but then we only need the vertical component in this case, so the E naught cosine portion. But again, because intensity is related to the electric field squared, we end up with that cosine term squared when calculating intensities. So let's say we have a situation where we have unpolarized light. So it consists of all possible directions. But if we have unpolarized light shining on a filter, so the filter axis is vertical, but then we have it shining on another axis. Let's say this new axis is 60 degrees from vertical. So this is our axis. So light shining through both of these filters. If the original intensity is I naught, what total transmitted intensity do we end up with by the time the light has passed through both filters? Well, we need to look at this one filter at a time. We know that unpolarized light passing through this first filter will result in polarized light that lines up with the axis of this first filter. The intensity, I'm going to call this just I1, the transmitted light intensity after coming through filter number 1 is going to be half of what the original intensity was. This light is now polarized, and this light is shining on filter number 2. Well, because we're starting with polarized light and shining it on a filter, we need to use this equation here for our polarized light. This is called Malice's law, in case you want to know the name of it. This polarized light that we have after coming through the first filter can be thought of as having a component that lines up with the axis of the filter and a component that's perpendicular. In this equation up here, theta is always the angle between the polarized light and the next filter axis, the filter it's going to go through. So our light is polarized vertically. This is our polarized light. The axis filter we draw first, so the angle I care about is the 60 degrees. I'm going to call this I transmitted I2. So the intensity of this light that makes it through, in our equation, I naught means the intensity of the polarized light. So the original polarized light, the intensity it has. That means, oh, sorry, I don't know what I just pressed. what our equation ends up looking like is I1 cosine squared of theta. Why it's I1 is because I need the intensity of the polarized light that is shining on this filter. So the intensity that is transmitted through will equal half of the original unpolarized light times cosine squared of 60 degrees. Well, cosine of 60 is 1/2, and that cosine of 60 has to be squared. So 1/4, so we're getting 1/8, write that better, 1/8 of the original intensity through both filters, where I0 specifically represents the intensity of the unpolarized light that was shining on the first filter. So the first filter takes out half of the intensity, the second filter takes out more. Now it is possible, kind of an interesting thing, that if we happened to have unpolarized light shining on first a filter axis that was vertical and then a filter axis that was horizontal. So unpolarized light, we would get polarized light with half the original intensity through the first filter. But now, because the angle between the polarized light and the axis of the filter is 90 degrees, cosine of 90 is 0. No light will be transmitted, because there's no components of this light that lie in that horizontal direction. But it turns out we can have the vertical. If we place a filter in between these two, that is at some angle between vertical and horizontal, some light will get through. And that's because this unpolarized light of I0, as it passes through the first filter, it is now polarized up and down, the same as the axis of this first filter. When it comes through this second filter, we now have an angle in here that's not 90 degrees. The light that makes it through is going to be lined up with the axis of this second filter. It won't be as bright. Some of the intensity is cut out. So this I1 would be half of I0. This one, I2, would be the intensity of I1, the light shining on it, times the cosine squared of whatever this theta is. And then we have another theta here. Call it, what, theta 2? The intensity that comes through this last filter, 3, would be whatever I2 equals times cosine squared of this theta 2. So each filter rotates that electric field a bit. And so some light will get through. This is not the only way to explain this. I found a video clip just so you can see this. They are explaining it in terms of other effects, but what we see and we can explain what we see in terms of these equations here. I want to show you the little video clip just so you can have a visual to go along with this.
Here I'm playing around a polarized light. Sunlight is unpolarized, so it doesn't really matter what angle that if I use a polarizing filter. If you have two filters and they're polarized in the same direction, then essentially nothing too interesting happens. If the polarizers cross, then essentially the light making it through one filter is horizontally polarized. Then the next filter only lets through the light that's vertically polarized, so cumulatively nothing makes it through. This is used to have adjustable filters in photography fairly often. Now, something really interesting starts to happen, and in fact a quantum effect begins to kick in if I ask three questions. So, surprisingly, the answer I get depends on the order that I ask the questions. So, if I have a horizontally, diagonally, and then vertically polarized, I get a different answer than if I ask horizontal, vertical, or horizontal, vertical, vertical. So in between, I actually get a lot more light transmission than you would expect.
Okay, did you see when he has that middle one in between at an angle? You should be able to see that background a little bit, not bright, but a little bit. So watch for that.
Vertical, vertical. So in between, I actually get a lot.
See right there, you should be able to see that horizontal white from the paper or whatever's in the background. We get some of that light passing through. And that's just because of how these axes are oriented relative to each other. Now, he mentions photography. In photography, if you have a really nice camera, you may very well have some polarizing filters. And that can help reduce reflections and glares off of surfaces, so that doesn't impede your pictures. Another example is any type of conductor. When light reflects off of a conductor, it becomes partially polarized, or if it's a good conductor, it becomes completely polarized. And polarizing sunglasses can cut out that polarization. I think there's a picture in our book, so I'm going to grab that really quick to show you. So this picture from our textbook is a bowl of water with some little rocks in it. When light reflects off of water, which just regular water, not pure water, just regular water from the tap, is a good conductor. Light becomes polarized, reflected light does. And so the reflected light is polarized horizontally. This filter that they have, they show this line that represents the axis of the filter. And so since the axis of the filter is also horizontal, all of this reflected light makes it through. So we're looking at the reflected light. In the bottom picture, with this axis of the filter oriented vertically, if we think about our polarized light being horizontal, but our axis being vertical, when we set up our equation for the transmitted light, the angle between our polarized light and the filter is 90 degrees. If this is 90 degrees, we don't get any light, we don't get any of the reflected light through. And that's why we can see these rocks well. The reflected light is cut out, which allows us to see into the water nicely. So if you're a fisher, you like to go fishing, or even just water sports in general, that would reduce the glare and the reflection off of the surface, and it just cuts out that glare, and you can see into the water if you're fishing. So polarizing sunglasses can be helpful. Back when bumpers were conductors, when they were metal, they would actually cut out reflection off of there as well. Now, my polarizing sunglasses, I see checkerboards on the windshields of a lot of cars, so the windows must be polarized to some extent as well, or have polarizing filters over them. Polarization. So for us, the polarizing sunglasses, or if you are a photographer and you have a nice camera, you likely have a polarizing filter to take your pictures as well. I'll go through a few example problems, and then that's the end of this particular chapter, 31.